In this lecture, we'll be generalizing the chain rule to functions of several variables. I want to start by modifying how we think about chain rule to kind of relate it to this generalized version of chain rule, or to make an argument to show that the chain rule in Calc 1 is can be viewed as this. So this is kind of different. First of all, well, we definitely remember chain rule, at least I hope we all do. So what happens is in the Calc 3 version of chain rule, there's a change in perspective, which is kind of specified down here. So in the Calc 1 version, we're actually we're used to viewing we think of the chain rule as being the derivative of this composite function f composed with g, and then we know about the derivatives of f of x and g of x, and so then well, we kind of stack things together. For the multivariable chain rule, we actually end up thinking about it differently. We instead think about the composition as being the idea that f is a function that depends on g, and f is the function that depends on g, and g is a function that depends on x. And so, instead, what happens is our way of thinking is different. So notice that f is a function depending on g, not f of x, and then like stacking together as you would in Calc 1. So instead we have this kind of relationship, and there's sort of a dependency diagram that looks like this. And the way that we read off chain rule from such diagrams is that for each arrow, we think of it as the relationship as being a derivative. So if we're trying to create the rule for taking the derivative of f with respect to x, what we do is, well, we have to pass through g, so that, and then we pass through from f to g, and then from g to x, and each of these edges is a derivative. So we do df dg and then dg dx. And notice that here I'm using straight d's. We'll be using curly d's shortly. So that's just dependent on whether the function is a function of one variable or of multiple variables, whether we use the straight d or the curly d. Right. So notice the weird thing is that when we write it like this, we end up with this funny quantity df dg, which is maybe not what you expected. Although this total rule kind of looks familiar. This should look like I believe it's called a Leibniz rule, kind of the idea of things canceling, right? And then here I'm just making an argument of why this actually makes sense. I'm actually relating why dfgg is actually this composition. So the idea is that this symbol, this expression, or this sub-expression, f prime of g of x, is you're taking the derivative of f with respect to x, and then you're plugging in g, or you're composing with g, which ends up being this. But composition actually is a variable rewrite. You're replacing x by g in the expression. That's what it means to do the composition. You're replacing the variable, and so then you end up switching df dx into df dg, and so there you go. So a bit of an argument for why this works. Okay. Now let's take a look at the generalized chain rule. So we're going to start with small examples of this before we then get to the fully generalized version. So suppose that we have f, a function of two variables, x and y, where we then think of x and y as being functions of a variable t. So the book does this kind of thing with notation, g of x and h of t, which kind of separates things out even further than necessary, but I would just think of it as, like, say, x is a function of t, and y is a function of t. That might be a easier way of expressing this, and in fact, that seems to be what the book does here, so I'm not sure why I did that there. But so we end up having this kind of relationship between symbols. So the function f of x, which for whatever reason the book calls z, Well, okay. First, this kind of composition, you can see that f depends on x and y, and x and y both depend on t. So when you kind of nest everything together, you see that f ultimately can be thought of as a function of t, if we were to like do those compositions. So then the way that it works to create the chain rule is, well, you have this kind of relationship among the variables, f, x, y, and t, right? So f depends on x and y both depend on t. The book separates these t's out to make it so that these are actually trees, but the way that I will end up drawing things shortly, you'll see that is that I would draw it like this, y, and then they both end up depending on t. And so, but what you do is, yeah, with the different edges, you're taking derivatives. So notice that f connecting with x and f connecting with y, you're taking partial derivatives with respect to x and y. But then for these, because x and y are both functions of just one variable, this derivative is a straight d derivative. And what you do to get the final chain rule, which is this, maybe I can just use a highlighter for that. I think it's a separate button. Yeah, so for this, oh, okay, well, that's a bit, I don't like that. I don't know. Yeah, so for this, what you do is that you add up across all the paths to get to the variable that you're taking the derivative with respect to. So we're taking the derivative with respect to t. There are two ways to get to t. There's a path that goes through x and a path that goes through y, as you can see. And so each path, we end up taking the products of different derivatives, and then we sum across all paths. So we have a path dz dx, and then a path dz dx, dx dt, and a path dz dy, dy dt. Okay. And then with so this one, no, we have a slightly more complicated example. So f is still dependent on x and y, but this time we have x and y are both functions of u and v. So instead of functions of one variable, they're now functions of two variables. If we push the functions x and y in to f, we end up with this composition, which means that we can view f as a function of u and v, and we can take partial derivatives with respect to u and v. This is a tree diagram that depicts all of the relationships. So f ends up depending on x and y. X depends on u and v. Y depends on u and v. If I were to draw it in the other way, it would be, let's see, f depends on x and on y, and then you have another layer of variables, like that, like so. So you have that x depends on u and v, and y depends on u and v. Okay. Right. So from that, we can read off maybe I'll scroll out a little bit just so that we can see. It's a little bit difficult. Well, you can read it off from there, but this is part of the image. This is part that I typeset. So dz du and dz dv can be computed. Z, for whatever reason, the book switches letters. I would just call it df du and df dv, but it calls it z. So, okay, well, if we're taking the u derivative, then there are two ways to get to u. There's a way that crosses through x and a way that goes through y. And in this tree diagram, it would be this branch and that branch. So you have a dz, dx, dx du, and a dz, dy, dy du, which is the first line there. And then for the derivative with respect to v, same thing. You have two ways to get to v, from one going through x, one going through y. So you could do df dy, dy dv, or df d, or I think I said it the other way around. df dx dx v and df dy dy dv. And of course, instead it uses z instead of f, but that's fine. Okay, so yeah, this is what I was saying. So instead of trees, as the book does, we can just do a graph, a general graph of the connections between things. So f depends on x and y, x depends on s, t, and u, y also depends on x, t, and u. So this diagram is depicting this kind of situation. You have x a function of s, t, and u, y a function of s, t, and u, f a function of x and y. And so f, ultimately, if we do those compositions, f depends on s, t, and u, and we can take partial derivatives with respect to s, t, and u, which you would then be able to do. And I've written them out there. Okay, so for the general chain rule, now, it's the same idea, basically, just generalized to arbitrarily many variables, and well, in this case, it only has 2 layers, and I actually specify, I show you that you can do it with more layers as well. So notice that you have f, you think of it as a function of n variables, x1 through xn, and each of these x1 through xn's, you can, if they are functions that are of variables t1 through tm, then that means that you can take the derivative of f with respect to t1 through tm. There are those partial derivatives. In order to do that, you would have to sum across all the paths that you could take from f to the t sub m variable that you are thinking about. So you end up with this kind of formula. So you can see that you have these intermediaries, x1, x2, up to xn, and you're trying to take the derivative with respect to some t sub k for some k. The k can vary from 1 to m. It's just specifying which target node you're aiming towards. Okay, so now, yeah, this is just an example of generalizing not just the breadth, meaning how many variables your function depends on, but also like how composed they are. So in the Calc 1, you saw that if you had a composition of 3 functions, you would have the chain rule kind of extending in this way, where it's f prime, the derivative of f of g of f h of x, f of g of h of x. Its derivative is f prime of g of h times g prime of h times h prime, right? You should have seen that and probably worked with it to some extent. So in Calc 3, well, we can do all kinds of things. So suppose that you have a function u that depends on a function of 3 variables. X, y, and z are functions of 2 variables, w and t, and then w and t, let them be functions of 2 variables, the variables being r and s. So you ultimately would have this kind of diagram relating things. And so if you wanted, say, to create the derivative of u with respect to s, well, there's a lot of different paths you could take. It ends up being 3 times 2 paths, because we have all the relations between all the different layers. So you can see that we have 3 choices for the first layer, and then 2 choices for the next layer, and then we're forced to take s because we're taking the derivative with respect to s. So that ends up being 6 different paths, which ends up being 6 different terms. And then the fact that there are 3 factors is because the paths are of length 3. So you've got one path from x to w to s, one path from, let's see, what's another one? From z to t to s, or maybe z to w to s. You can see that there's a total of 6 different paths, and that ends up being these 6 terms that I've typed up. Definitely not going to read that. Okay. Now let's see an example. So I wrote down 2 examples, one that is slightly easier, one that is slightly more complicated, similar to your homework exercises. So in this one, we have that the function f is a function of two variables, and then the variables x and y are functions of one variable, the variable t. And you're asked to calculate dz dt. Okay. So in this one, we sort of we have different d's. We have a curly d and a straight d because x and y are functions of one variable. So the derivative for those functions use the straight d version. Okay. All right. So let's see. I think that the chain rule is pretty clear. Maybe just in case, I'll draw the diagram of it. So z. Did I use z or f? Okay, I kind of switched from z to f. So I'll say z is equal to f, and I'll just say they're both x and y, and they both depend on t. If you were trying to do it the tree diagram way, then this t would be two different t's connected to x and y. Okay. All right. So from this diagram depicting the relations between the variables, the derivative of z with respect to t is going to be df dx times dx dt plus df dy times dy dt, right? Which is what I've written there. And then you go ahead and compute those derivatives. So I would think that the derivative isn't too hard. So df dx and df dy, you're taking the derivative of the square root function, and then you have your typical chain rule from Calc 1. So the chain rule will then, with respect to x, is going to put a 2x in the numerator, as you can see here. Right? This 2 comes up from taking the derivative of the square root function. And then the df dy, you get a minus 2y, since the y has a negative there. Okay, so those are the partials. Now for the dx dt and the dy dt, that's straightforward. These are exponential functions, so you have a small chain rule within there to make the 2 and the minus 1 show up. Okay, so, I didn't mean to box this one. I actually meant to box, not this one, but this one is what I meant to box. So, what can happen is that, gosh. So what you consider to be the answer to this type of question can depend on, it depends on whether you really want to enforce the variables going down to be at a consistent layer. So notice that the way that this is written, you're kind of mixing variables of different layers. You have x and y and t, but x and y are functions of t. So one thing you can do is to kind of do the composition to bring the variables down to the same layer, which is what I do next. So first I simplify. I think that's just collecting things together, and then you can replace. So you have that x is e to the 2t and y is e to the minus t. So then just replacing those in, and then simplifying. Notice I simplify on the top as well as on the bottom, so that ends up giving you this expression that it's all in terms of the variable t. Okay, so that's the simple example for chain rule. This is a slightly more convoluted example. So we have w, a function of 3 variables, x, y, and z, and x, y, and z are all functions of 2 variables u and v. So the diagram for this would be w depends on x, y, and z, and x, y, and z depend on u and v, which ends up being kind of messy. We have 6 lines here, right? All 3 of these are connected to those. All right, so yeah, computing dw du would have 3 different terms, right? Because they pass through x, y, and z. So you have one that passes through x, y, and z. and then you'd compute those derivatives. Now the partial derivatives with respect to w, or the partial derivatives of w, I should say, are pretty straightforward. So dw dx is 6x minus 2y. dw dy is minus 2x. It only contributes from this term. Or the only term that contributes is this one. And then dw dz is going to be only this term. It's going to be 8z. So you have that. And then computing the other partial derivatives that you need, let's see. So the ones for u are going to be, well, okay, they're exponentials. So all of these stay the same. But if I take the partial derivatives with respect to v, then this becomes e to the u times cosine of v, and this one becomes e to the u times negative sine of v. Right? So you could compute all those partial derivatives up front and then plug them in. I've kind of just laid them out together. And so the first box equations are kind of the answer if you don't care about getting things to be in a consistent layer. I would say that those are perfectly acceptable as answers. But if you want to make them be in the same layer, then you have to substitute things in. So notice that, yeah, we have x and y's here, and z here. And in this one, we have x and y. So you have to sub those in with the definitions that you're given. And then simplifying allows me to write it in a slightly better looking format. Okay, so that's 244. I think yours is about the same level of difficulty. Yeah. Okay. Right, and so now there's a topic we can revisit that is the implicit differentiation. So hopefully you remember how that worked in Calc 1. The idea was you're given a function. Well, you have like y that you can think of as a function of x, but you're not able to solve for it in terms. You're not able to isolate y completely. Instead, you just have this kind of relationship. So I don't know. What's an example? Maybe x cubed, y squared is equal to x cubed plus x, y. Something like, maybe something like that would be an example. And then to get it into this form, we just like move everything to one side so that we have the other side equaling 0. Then the way that implicit differentiation worked was we just tacked on this additional rule saying that whenever we encounter a y, its derivative is dy dx, the special symbol dy dx, and then you solve for dy dx and just juggle the equation around. Okay, so what happens is that now that we have partial derivatives, we're actually able to get a faster way to compute this implicit derivative. But first I talk about what this says for higher variables. So in this higher variable case, say that you have f of x, y, and z, a relationship between these three variables, and you're trying to think of z as a function of x and y, although you're not able to solve for z explicitly. Well, what you are aiming to do is say compute, say you're trying to compute dz dx, or dz dy. What you can do is first you take the derivative of this implicitly, and with respect to x, let's say, because this is a function of multiple variables, there's a chain rule involved. So you would have this coming out from chain rule. F is a function of x, y, and z, and x, y, and z, we're going to take derivatives of them with respect to x, and then we have something nice showing up. So what happens is, in this case, we're trying to solve for this guy. We're trying to solve for dz dx. and we end up having these other two terms. So you could move them over to the other side, and then divide by df dz in order to solve for it. But this actually simplifies a little bit. So dx is just 1, right? That should be pretty clear, pretty intuitive. The other thing is that we can actually say that dy dx is equal to 0. Now the reason that we have that is because we assume that x and y are independent variables, and so the way that y changes with respect to x is it doesn't. They're completely independent of each other, so that partial derivative is 0. Okay, so that allows us to get rid of this middle term, and so you end up with, and this becomes 1. So that simplifies to give you this is equal to 0. And then rewriting the partial derivatives to use subscript notation instead, we end up with this equation. Finally, you solve for dz dx, and that's going to move the f sub x over to the other side, divide by f sub z, and so you end up with this expression. Okay, so that's just deriving for you this formula. You could just take this as a given, and similarly, we have this relationship. Okay. Now, how does this relate back to the implicit derivative of Calc 1? Well, now that we have partial derivatives, let's think about this and take the implicit derivative of this. So little f is a function of two variables, and so we would take the partial derivative, okay, with respect to x and respect to y in taking its derivative. And then say we're thinking of y as a function of x, and we're aiming to calculate dy dx. So we're aiming to calculate this guy. Okay, so like in the previous case that we discussed, dx dx is 1. Dy dx is not 0 in this case, because this is actually the thing that we're solving for. And we do have kind of the relationship. We're thinking of y as a function of x. Although we're not able to solve for it explicitly. Okay. So, right, then, yeah, so this is the step of just getting rid of that dx dx, and then you move to the other side and rewrite the expression in using subscript notation just because it looks nicer. So you have f sub x divided by f sub y, and then with a negative. Okay. So this formula ends up being used in one of your problems. And yeah, just notice that this, now that we have this operation, the partial derivative, we can actually express the process of implicit differentiation in a simple formula, rather than that process that you used in Calc 1, where you had to, I guess the steps where you took the implicit derivative, then you gathered terms that had dy dx in them and terms that didn't. You grouped them to two different sides of the equation, and then you divided. You then factored out dy dx, and you divided over the rest of the equation. It was a 3-step process, which ends up being compacted into this simple formula. So you don't need to run through a 3-step process. You can just use one formula for it. That's kind of nice. Right. So yeah, and here's an example of that. So I don't know if I want to actually relate back to the other version. So I guess I can. Yeah. So using the formula is simply just recalling it and then just doing it. Right. So the derivative with respect to x, the partial derivative with respect to x will be 6x minus 2y plus 4, as you can see. And for the derivative with respect to y, partial derivative with respect to y, minus 2x plus 2y minus 6, which is there. And then I think I multiply the negative into the denominator, and then I factor, I cancel by 2. Everything cancels by 2. Okay, and yeah, the long form process of this would have been let's see, what was it? Yeah, the calc 1 way would have been that you 6x minus 2. Now then you have a product row here, so then you would have like y plus uh, xy prime is no, plus 2 y prime plus 4 minus 6y prime is equal to 0. And then you'd group everything with a y to one side, and then everything else goes to the other. So let's see, this gives me a minus 2x plus 2y minus 6 is equal to minus 6x plus 2y minus 4. And so then you end up with y prime is equal to minus 6x plus 2y minus 4 all over minus 2x plus 2y minus 6. And it looks like I have a lot more negatives to cancel, and I have 2's to cancel. But yeah, if you negate everything and divide by 2, I think it'll give me the same answer. Plus 4, oh, wait, no, I divide by 2, plus 2. Over, nope, 2 becomes 1, x minus y plus 3, is that right? Yes. Yeah, okay. So the 3-step process from Calc 1 became a single formula that you can just compute. Okay, I guess that's it.